Yeah. So, children, I hope the screen is being shared and everybody is able to see. Just give me a confirmation. Okay. So we'll start off. I already have kept things ready because I joined early today, so I started writing the notes. Fine. So we'll go ahead. I hope I'm audible as well as the screen is visible. What I'm sharing, right? All right. Good evening, children. Once again, welcome to an interesting session, in association with Igniting Young Minds. So we are now starting with the next chapter, which is, electrostatic potential and capacitance. Previously, we learned electric fields and charges, and we have seen a couple of questions based on that. And now we are moving on to the next chapter, which is electrostatic potential and capacitance. So this is the chapter that we'll be looking at. So we'll brush up some basics. So it is basically a continuation of electric fields and charges. So it is all the concepts are almost overlapping. So it is easy for you guys to understand. So the first concept that we'll be seeing is potential difference. Okay. So now this concept of potential difference is very simple. It's easy to understand. As the name suggests, when you say potential difference, potential means it is something with reference to difference in height. Whenever there is difference in height, we say it is potential. I hope you guys are able to correlate with the concept of potential energy. Now, when do you say that there is potential energy? The energy possessed by an object due to a certain configuration or due to a certain height, isn't it? We say that there is potential energy. Now, who can tell me which scenario? I'll give you two examples where there is a greater potential energy. You tell me. Water in the underground tank, first case. Second case, water in the overhead tank. Now all of us live in flats or apartments. We have two tanks. One is underground tank, and or we also call it as the sump in common language. And one more tank is overhead tank. So both has water. Now which one has a greater potential or a greater potential energy and why? Yes, children, you can tell me. So that is the concept. Where does the water have a greater potential? Is the underground tank water having a greater potential, or overhead tank having water is going to have a greater potential? And why? Yes, feel free to communicate. Yes, Puntamla Risi is there. Then we have Mutusami. Anybody, you can volunteer. You can tell me which has a greater potential or a greater potential energy. I gave you two cases: water in the underground tank and water in the overhead tank.
So
Are you able to
overhead
understand what
tank
is
is
water
the
in overhead?
overhead tank will have better more energy.
Overhead tank, more
Yes.
energy, because it is at a greater height. As height increases, we say that the potential also increases. Now this concept can be easily understood. Now we Coimbatore is very close to different falls, right? You have Monkey Falls, you have so many falls in and around Coimbatore. Now you know how water flows it down the falls. It always flows from the region of higher potential to the region of lower potential, right? Water will only come downhill. It cannot go uphill. That is not possible, right? Because it has to do work against gravity. So gravity is always going to pull things downwards. So therefore, something at a certain height, that is be it water or any object which is kept, so will have a greater potential energy because it is at a greater height. As height increases, potential is going to increase, and so does the potential energy. So that's the concept which is involved here. So potential difference means the work done in bringing a charge from one point to another against electrostatic forces. That is called as potential difference. So that is given by the symbol V. So V stands for potential. Okay, the potential, or you can say potential difference, is equal to W upon Q, where W is the work done in bringing a charge, okay, from one point to other against electrostatic forces. So W upon Q. So this is the formula. So the unit of potential difference is volts. The unit of work done, I hope you guys already know. We have learned even in 11th standard, which is joule. And the unit of charge is coulombs. So technically speaking, 1 volt is equal to 1 joule upon 1 coulomb. So that is the relation. So we'll move on to the next part. Electric potential due to a point charge. To make things very simple, so I have taken the previous chapter's formula, and I have derived the new relationship here. Okay, so just now we learned electric potential or potential difference is work done by charge. Just now I introduced the concept V is equal to W by Q, which is equal to, I hope you guys know that work done is equal to force into displacement, which you already know, right? Work and energy chapter. So work done is nothing but the product of force F into displacement, which I have written as R. So F into R divided by Q. Now, what is F? I hope you guys know Coulomb's formula, Coulomb's force formula, which we learned in the previous chapter. So F is equal to K Q1 Q2 by R square. So I have substituted that here. Okay. So this came from Coulomb's force formula. Okay. K Q1 Q2 by R square into R by Q. Then what I'm doing, I'm cancelling one R with R square, and Q1 and Q2 both are equal to Q because we are referring to a single point charge, not multiple charges. So therefore, I'm replacing Q1 and Q2 with Q. Upon doing so and simplifying, we get the relation for electric potential due to a point charge as V is equal to KQ by R, and that is how it came. Okay, so it's very, very simple and easy to understand. So this is the formula for electric potential difference or just electric potential due to a point charge, wherein V is equal to KQ upon R, where K is nothing but a constant. I hope you guys know the value of K. When you solve numericals, you will take the value of K as 9 into 10 power 9. Okay, Q is the value of charge in coulombs, which will be given in the question. R is nothing but the distance from the charge with respect to which you would like to calculate the electric potential. Okay, that is the value of R. So this is all about electric potential due to a point charge. Okay, I hope this part is also clear, children. Here also the unit of electric potential is volts, unlike the previous one. It is always same, it will not change. Okay, just the formula is different, that's it. Previously we had used work done relation. Here we have used relation in terms of K, Q and R. Moving on to the next concept, electric potential due to a dipole. Now, I hope you guys know what is meant by a dipole. The word dipole itself indicates that there are two polarities. Di meaning two, pole meaning polarity. So when you have two charges which are equal in magnitude but opposite in signs, separated by a finite distance, then you call it as an electric dipole. So I have two charges, minus q and plus q, placed at points A and B as shown in the figure. The distance between A and B is called 2A, which is called the dipole axis or the dipole length. Okay. Now let me take the midpoint of the dipole as O. Now if I say O is the midpoint, I hope you know midpoint will bisect AB into two equal halves, meaning AO is equal to OB. And both will be equal to A. Okay, that only then if you add will you get 2A, right? Logically speaking. Now, we would like to find out electric potential at a general point due to this dipole. Meaning, I'm going to locate a point P. Okay, say I'm locating a point P, an arbitrary point P. I'm showing it here. I'm going to locate this point at a distance of R from the midpoint of the axis of the dipole O, such that OP is equal to R. Is that clear? Now, what is angle theta? Angle theta is nothing but the angle made by the dipole axis OP, okay, by the length OR. That is, by the length. You can also tell this as the displacement vector. Okay, by the displacement vector R with the dipole axis. So that is angle theta. I repeat, angle theta is nothing but the angle made by OP, that is the distance, the general point with respect to which you would like to find out the electric potential. So that length with respect to your dipole axis. So that is angle theta. Okay. Now for this, children, there is a formula which tells you V is equal to Kp cos theta upon R square. So this is a general formula for electric dipole. Okay. So based on different values of theta, the formula will change. Okay. I hope you guys know cos function varies from 1 to 0, right? You guys are good at trigonometry. So cos 0 is 1 and cos 90 is 0. So For which value of theta will electric potential have a maximum value? It is going to be maximum for angle 0. It's going to be minimum for angle 90, as well as, I mean, even 180 also. I guess cos 180 is going to be -1, right? So it depends on the angle theta. Okay. With that, moving on. So here again, electric potential, the SI unit is in volts. When I say potential, it is obviously going to be in volts by default. Okay, that's the third concept for the day. Moving on to the fourth concept. Here we are trying to relate, that is relation between electric field E and electric potential V. So we are trying to relate these two physical quantities V and E. So for that, what am I doing? I'm using the formula V is equal to W by Q, which is the first formula we learned. Okay, electric potential is work done in bringing a charge, okay, from a point against, the other. So W by Q. Next, work done is equal to force into displacement. I have substituted. Then what I have done is I have expressed force in terms of electric field as Q into E. Very important. So I have expressed Coulomb's force in terms of electric field, which is F is equal to Q into E. That is what I have done. And then I have simplified, got the relation V is equal to E into R. Okay. Now I'm shifting this R. Okay. So before shifting, I'm trying to differentiate on both sides. I'm differentiating on both sides. So when I do so, I will get dV is equal to E into dr. Okay. Because electric field is always constant. Electric field does not change. Under the assumption of uniform electric field, we can write dV is equal to E times dr. So therefore, we can write dV by dr is equal to E. Okay. So the potential gradient can be expressed as electric field. So this is also another important formula, children, very important. So E is equal to dV by dr. Okay, usually there is a negative sign which comes because always electric field is going to be opposite to the direction of electric potential. So this is a formula that relates electric field and electric potential. Okay, so that's the fourth concept that we are seeing for the day. Okay, so with that, let's move on to the next relationship. The next concept, fifth concept, let me just write it here. So next, moving on. Now we are going to see what is the potential energy of a dipole. Okay. So now we will see potential energy of a dipole in uniform electric field. So we are going to see what is the potential energy of a dipole in uniform electric field. Now for this also, children, there is a relationship. Okay, so a simple relationship. So first, whenever I say there is uniform electric field, I hope you guys know we represent uniform electric field by using parallel lines. Okay, so draw a couple of parallel lines like this, which indicates uniform electric field. Okay, so this is uniform electric field E bar. Now I'm going to place a dipole here. So say I'm placing a dipole like this. So there are 2 points of the dipole. Let me just mark it as A and B. So this part is A and this part is B. And I'm placing two equal and opposite charges. So I will place minus Q charge at A and I will place plus Q charge at B. And I hope you guys know the distance between A and B is 2A, which is nothing but the dipole length. Okay. So AB is equal to 2A. Okay. So this is all there. Now, whenever there is going to be a dipole that is placed in uniform electric field, we have learned in the previous chapter that it is subjected to torque, right? So I hope you guys know what is torque. The turning effect of force is called as torque. So the center of the dipole is this point O. So the charge plus Q charge at B is going to experience a Coulomb's force because F is equal to Q into E in the rightward direction. So F is equal to plus QE. So it will experience plus QE force towards the right. Similarly, the negative charge at point A will experience F is equal to minus QE charge, minus QE force in the left, towards left. So when there are two equal and opposite forces that are going to, operate along the ends of these dipole, then this dipole is going to experience something called as a turning effect, or which is called as a torque. Okay, so it will start to rotate about the axis of the dipole. And we have already learned the formula, so I'm not deriving it again. So I hope you guys remember it. So torque is given by the relation tau is equal to PE sine theta. Okay, this is the formula, children. this this T is actually called as tau. It's a Greek alphabet which is called as tau, TAU, tau. Okay, so tau is equal to PE sine theta as the formula, where P is nothing but the dipole moment, E is electric field, and theta is nothing but the angle made by your dipole with electric field. So this is theta. Okay, I'll just mark it here so that you can visualize it. So theta is nothing but the angle made by the dipole with the uniform electric field. Now coming to our actual part. Now what we are going to do here is, we want to find out not torque, we want to find out potential energy. So to find out potential energy due to this dipole, electric dipole in uniform electric field, so what we do here basically is we are going to integrate this torque, expression. Okay, so that's basically the work done concept. So we are going to apply the concept of work done, and then we are going to simplify. So as you guys know that according to work energy theorem, work done is equal to change in energy. It can be change in kinetic energy, or it can also be change in potential energy. Okay, so two different aspects. So that is a concept that we are going to apply here. So the energy, so work done is equal to change in energy. So here in this case, change in potential energy. So I'm going to express that as, so work done is nothing but, again, the unit SI unit is in terms of joules. So we can directly write the potential energy is equal to. So now here we go and express. Now when we go and express, it's very important to know that we are going to integrate. So when you integrate, you should be careful. So I'm integrating. Now when I'm saying that I'm integrating, you need to understand what are the factors of integration. Okay, so here, because there is a rotation that is involved, so as the electric dipole begins to rotate, it is rotating with respect to an angle. So don't you think as it rotates, the angle theta is going to change? Yes, of course it will change. So therefore, we express theta as a function, or express theta as our integrating factor, because that is what is changing here. Okay, electric dipole moment P is constant, electric field is constant, not affected. When the dipole rotates, begin to rotate, only the angle theta is getting affected, or that is going to change. So therefore, we will write potential energy as integration of tau into d theta. Okay, I'm going to go and express integration. As theta is changing, we can write this as theta 1 to theta 2. Okay, torque formula just now I wrote there, which is P E into sine theta into d theta. That is what we are doing. Okay, that's it. So now we go and simplify. Take all the constant terms out of the integration sign. So PE will come out of the integration sign. So integration of sine theta into d theta. Who can tell me what is the formula of, what is the integration of sine theta into d theta? Anybody is having any idea about integration? integration of sine x dx you would have learned. Integration of sine theta is actually negative cos theta. Okay, there is a formula, children. So in case you guys don't know, you have to learn the formula for calculus. So I write here integration of sine x into dx is equal to minus cos x. Okay, that is the formula. Cos x plus c, there is an arbitrary constant, but in physics we don't show that constant. Only in maths we explicitly show it. Okay, so here we write p into e into integration of sine theta d theta is minus cos theta. Now the limits I am applying, theta 1 to theta 2. Okay, so I'm applying the limits. This negative sign also I can take it out. So in fact I can write it as minus p into e, open the bracket, substitute the limits. Okay, so in the place of upper limit minus lower limit, that is what we will do, children. So we will write this as cos theta 2 minus cos theta 1. Now please remember this negative sign is there in the formula. Okay, in the formula of integration, when you substitute the limits, that negative sign will come. Upper limit minus lower limit. This minus has nothing to do with the minus which came before. Okay, the minus which came before was the minus which is in the formula by default, as you can see. Okay, so therefore be very careful with the signs so that you don't get confused. Okay, next what we do here, we can, so what we have done is you can also take the negative sign inside and write, or you can just leave it at this. So this is the formula for the potential energy due to the dipole. Okay, so it is given by the symbol u. U is a symbol for potential energy. That's it, children. So this is the formula for the potential energy of a dipole in uniform electric field. So we have derived this relationship. Okay, where theta 1 is the initial angle and theta 2 is the final angle until which it is rotated. Okay, usually initial angle will be 0 by default. If not, it will be specified in the question. So as per the question, you will have to approach. That's it. Okay, so I hope this concept of potential energy of a dipole in uniform electric field is clear to all of you. So with that, we'll move on. So almost we are, finishing the initial stages of electric potential. So electric potential part is now finished. Now we are moving on to the next part, which is called as capacitance part. Okay, so we'll see what is the capacitance part now. So that is the sixth concept. Okay, concept number 6. Now coming to the capacitance part. So before going deep into the concept, have you guys heard about what is a capacitor? Okay, I'll just write it here. Capacitor. What is a capacitor? Have you heard about this term before? Or do you know what a capacitor is and where and all it is used? Any common idea? Or do you even know how it looks like? Okay, so capacitor is, it is a energy storage device. So anybody has heard about capacitor? Somebody is familiar with it, or is it something new to you guys? Have you heard about capacitor, children? In our daily life, every day we are using fan, ceiling fan. Have you seen that white cylindrical part in the ceiling fan? Whenever the mechanic comes, if your speed of the fan is going to get reduced or it is very very slow, then capacitor needs to be changed. Okay, so there is a component in the fan, in the ceiling fans, which is called as a capacitor. All right, so that is actually it is a device, it is an energy storage element, we say. Okay, it's an energy storage element. So this capacitor has got so many different uses in our day-to-day lives. They are used even in many circuitries. In heating elements we have circuit boards, we can see capacitors which are embedded. Okay, in electronic devices you can find them, refrigerators, everywhere you can find capacitors. Okay, so they have a wide variety of applications. Okay, main application of a capacitor is to store energy and to discharge them at a required rate. The discharge rate is typically very very high. It can discharge energy at a tremendous rate. Okay, so suddenly energy is required. You want to start a motor suddenly, it is not possible because we don't have that much amount of energy that can be supplied immediately. So that is where a capacitor comes in. So this capacitor, what it does, It can store the energy and it can discharge it at a higher rate, at an exponentially higher rate as per the demands of a device. So it can be used to start a motor, start a generator. So everywhere, capacitors are typically used. Even your fan. The fan can even work without a capacitor, but to achieve the desired, speed, it will take a lot of time. Probably without a capacitor, your fifth or fourth speed, you must wait for half an hour. Okay, which we don't have that much patience. Yo, in during hot summer day, we want that speed, or you want that much amount of speed, right? So that is achieved because of the capacitor. You also have a regulator, so you can regulate it. You can regulate the speed by using a regulator, okay, and which is also connected to the capacitor. So as and when it discharges, you can see that the speed can be controlled. Okay, so its discharge rate can be controlled by using a regulator also. So this is all about the capacitor, children. So capacitance and capacitor are basically the same terms. In physics we will be calling them as capacitance, okay, which is as a circuit element we will be dealing it. Okay, the symbol for a capacitor is like this. We draw it by using two parallel lines. This is how it looks. I repeat, it is parallel lines. You should not draw one big line and one small line. This is not a capacitor. We call it as a cell. Okay, so most of them have a common misconception. They think both are the same. No, it is not. This is different. The left one is different, the right one is different. The left diagram that I have drawn is a capacitor. I mean, both lines should be of same size, okay, same length. Parallel lines, two parallel lines. If you're joining together by using lines on the left and right, then that is a capacitor. On the right side, one big and one small line, if you are joining and you're showing it with connecting wire, then this is a cell. This is called a cell. Okay, so both of them are different. A cell is a source of potential, but capacitor is a device which can be used to store energy. Fine. So now we'll go on. You have some interesting information about capacitor. I hope you have some idea now. A capacitor can be easily built by using two metallic plates, okay, connected to a wire to a cell or a battery. So you can build a very simple capacitor at home by taking two metallic plates, conducting metallic plates, and you connect it to a cell or a battery as shown along with a plug key. Okay, so we have here successfully built a capacitor circuit. So the cell is supplying some potential V across the capacitor. The capacitor is given by the symbol C. C is what is capacitor or capacitance, you can say. Okay, and once you are connecting this cell or battery to a capacitor, now you can see here the capacitor is having two plates. I told you, let me call this left plate as A and right plate as B. I repeat, the capacitor is made up of two plates, two conducting plates. One is A and one is B. Okay, they are having the same material. Now, the plate A is connected to the positive terminal of the cell. So what happens? As you switch on the circuit, the plate A becomes charged. Agreed? Because you're connecting them to a potential, so they become charged. What type of charge will accumulate on plate A? The plate A will get accumulated with positive charge because it is connected to the positive terminal of the cell. I repeat, plate A of the capacitor or one side, left side plate is getting positively charged because it is connected to the positive terminal. Similarly, the plate B will become negatively charged as it is connected to the negative terminal of the cell or the battery. So there are charges Q that is developed which is equal and opposite on both the plates. Okay, so there is a charge accumulation. Because there is a charge accumulation, there is an electric field that is going to be set up between the plates of the capacitor, which helps in its conduction. I repeat, due to the accumulation of charges, an electric field is set up between the plates A and B. Okay, same thing if we are going to zoom, it looks like this. So the plates A and plate B. Plate A is positively charged. Okay, so this is positive. I'm showing positive charge here, children. Same thing, I'm just drawing it, little big. And plate B is negatively charged. Okay, fine. So this is A and this is B. Now, the charges are Q only. by default it is there, you can say plus q, and here you can say minus q. Okay, charge is in coulombs. Now, because they are having positive and negative charges that are developed, there is an electric field that is going to be set up between these plates, which is directed from positive towards negative charge. So there is an electric field that is developed. Why electric field is developed? Because there is a difference in potential. Agreed? Because there is a difference in potential, there is an electric field that is going to be developed. How come there is a difference in potential? And plate A is connected to positive terminal, which is at a positive potential. Plate B is connected to the negative terminal, which is at a negative potential. Are you understanding? So due to the difference in potential, there is a positive and negative charges that are developed between the plates. And hence, there is electric field that is set up between the plates that makes these plates or of the capacitor, conductive. And that is how conduction takes place between the plates of the capacitor. Okay, so this is a very important concept. Now, coming to the main, idea, the charge that is developed here, Q, is directly proportional to the potential difference that is applied. I repeat, the charge developed across the plates of this capacitor is directly proportional to the potential that is being applied. For example, say if I'm connecting a 2-volt battery, 2-volt cell, then whatever say I'm getting a charge of 5 coulombs. Okay, for 2-volt cell that is connected, I am getting 5 coulomb. Now imagine what will happen if I connect a 10-volt cell. Will the charge be less than 5 coulombs, or will it be more than 5 coulombs? I've increased now the potential difference is now increased. Then what will happen? Charge is also going to get increased. So this is the concept that you should know. Just like Ohm's law, where potential difference is directly proportional to the current, here the potential difference is directly proportional to the charge that is developed across the plates of the capacitor. So this is a concept that is involved. Okay. Now I'm removing the proportionality sign. I hope you guys know, whenever you remove a proportionality sign, we introduce a constant of proportionality. So we can write Q is equal to C into V. The C is called as capacitance. Is that clear? The stands for capacitance of the capacitor. Okay, so this is the capacitance. Okay, V is potential difference in volts, Q is charge in coulombs. As you know, by default, you have learned that. That is the same. Their terms remain the same. The new terminology that we are learning is capacitance. So when I rearrange this for C, I will get C is equal to Q by V, where Q is charge in coulombs and V is potential in volts. Okay, potential difference in volts. So the SI unit of capacitance is called farad. I write here the SI unit of capacitance is farad, F-A-R-A-D. Okay, it is named after the person who has found out. So there are different values or ranges of capacitance. I'll take 1 MF is discovered. So FARAD. Okay. So just 3 farad. Okay. That is 10 power minus 3 farad. 1 microfarad, mu F. Mu is nothing but micro. Okay. It's a Greek symbol. So micro means 10 power minus 6 farad. Similarly, 1 nanofarad, NF. 1 nanofarad means 10 power minus 9 farad. So that is nanofarad. Nano means 10 power minus 9. And 1 picofarad. Any guesses? 1 picofarad is nothing but 10 power minus 12 farad. You can see they are all, differences are all in terms of multiples of 3. 3, 3, 3, 3 difference. First it is 3, then it is 6, 9, 12. Okay. Milli means 10 power minus 3, micro is 10 power minus 6, nano 10 power minus 9, and pico is 10 power minus 12. So based on the question, appropriately you will have to use the conversion, factor of conversion, and then you will have to solve some numericals. So that's why this concept, this conversion I have taught, which is very useful. If at all you come across questions, I mean, you will definitely come across questions based on these configurations. You should know how to convert, okay, from milli to farad, everything in terms of farad and vice versa. So that's the agenda behind this. Okay, so I hope this is also clear to all of you. Okay, and the formula for capacitance is also clear. So I've introduced the concept of capacitance here. You know what is a capacitor, you know how to build a simple capacitor, and how does a capacitor conduct. Okay, and then what's the formula for capacitor, the relation between q, c, and v is also we have learned. Fine. So now moving on, we are moving on to the next concept, seventh concept, combination of capacitors. So capacitors have different combination, just like combination of resistors, which you would have learned in your previous grades. So we have combination of capacitors here. Okay, so we'll see combination of capacitors now. So capacitors can be combined, or you can connect them in different configurations. Okay, two different types you can connect them. What are the different ways of connecting capacitors or combining capacitors? The two prominent methods in which capacitors can be joined together are series combination, and the second one is parallel combination. So there are two different combinations. One is series and the other one is parallel. Now, what do you mean by series combination? Okay, series combination. I hope you guys have heard about serial lights. Okay, serial lights which are used in for decoration, or different ceremonies, right? So serial bulbs we say, serial lighting we say. LED lightings also we have nowadays. LED strips are also available, right? Have you seen the way how the small individual bulbs are connected? How the small individual bulbs are connected? They are connected one after the other. Have you guys noticed it? So that type of combination or connection is called as series connection. Okay, an example can be serial lights, connection of serial lights. Okay, and you can also see give example as the flowers in a garland is an example of series connection. Have you seen in a garland how the flowers are joined together one after the other? That's a classic example of series. On the contrary, you also have another type of combination which is called parallel combination. So now parallel combination, how the connections are done. When I say parallel, now something which is easy to understand is, have you seen a ladder? In the ladder, how the connections are made. If you have seen the ladder, it is one below the other. It's not one after the other. Okay, so when they are connected one below the other, that type of combination is called as parallel combination. For example, railway track is a classic example of parallel combination. You can see between two rails how the you can see how the ballast is kept. Okay, ballast is nothing but the cement stones which are kept between. So that is the example of parallel combination. Okay, that's an example. You can take the example of staircase. The stairs in a staircase is an example. The way it is connected is a parallel combination. So like that, you can try to understand what is parallel and what is series. So in series combination, it is connected one after the other like a train and all the compartments. So the connection goes like this. So this type of connection is called series connection. Say this is the first capacitor C1, C2, C3, so on until Cn. This type of connection is called as series connection. And in parallel connection, first you have C1. Now the next one I'm connecting below it, like this, one below the other, they are connected. This type of connection is called as parallel connection. Okay, I hope it is now clear. Okay, so this is parallel connection. We can call it C1, C2, C3, so on until Cn. Now there are certain important rules that you will have to follow to find out the total capacitance in both series as well as parallel, and I call them as the golden rules. What are the rules for series and what are the rules for parallel? In simple term, we will try to understand. Now, whenever I connect the capacitors in series across a cell or a battery, I'll take a cell, okay, along with a plug key, okay, and then when I switch this on, you know that there is some current that is going to flow. Let me call that current as I, okay. Now, do you agree that the current flowing through each and every capacitor in a series connection is going to be because whatever current is coming through the cell, the same current is going to flow through first capacitor, second capacitor, third, fourth, so on until the capacitor, because they are in series combination. It is one after the other combination. So the current is going to be same through each and every capacitor. So let me call the total potential here due to the cell or battery. Let us take that potential as V. You need to understand that here, when current of I flows through capacitors C1, the potential across it is V1. The potential across capacitor 2 is V2. Across the third one, it is V3. Across fourth one, it is V4. So on. Across the nth capacitor, it is Vn. So you need to understand this. The first golden rule. Potential across each capacitor is different in series combination. Okay, so I will write it here. In series, potential V across each capacitor is different. So this is something which you have to remember. So potential is different. Potential is different, but the charge the charge is going to be same. So charge across. So I will write the next rule here. Below it, I will write rule. Its previous statement itself I will. Well, charge across each capacitor is same. Charge across them is